Hello, this is David Tuschel, manager of the Raman Applications Lab at Hariba Scientific in Edison, New Jersey, and I would like to welcome you to another in our How to Raman educational video series. This particular video is about fast Raman imaging of few-layer molybdenum disulfide. And so let's begin by considering some of the important aspects of Raman imaging and the materials related to that, as well as the experimental details. The first thing, and the most important, is that the greater the contrast that one finds in the chemical bonding and the solid state structure in heterogeneous materials or samples leads to greater spectral contrast, which leads to greater contrast in the imaging. So spectral contrast and imaging contrast are intimately related. The second point is that the greater the spectral contrast, the faster one can actually perform Raman imaging. Now we get to the experimental details. The motion of the stage and the capture of the data in conjunction with the motion of the stage can be very important. The data that I will be showing you today and the images generated from them were acquired using a Hariba Explorer Raman spectrometer and with a Hariba Sincerity camera that for the 100, the 50, and the 10 millisecond integration times were controlled by Swift. And on the next slide I'll explain what the Swift mapping is. The areas that we mapped are 10 by 10 micrometer areas in 300 nanometer spatial increments with 532 nanometer excitation. And as I said, we're using Swift, and here are our integration times, and those are times per point. So 10 milliseconds, 50 milliseconds, 100 milliseconds, and 1 second per point. And finally, we'll show you how the application of a classical least squares algorithm, and there are other chemometric tools, can really help you in imaging, particularly fast Raman imaging. Here in this session, we're imaging the spatial heterogeneity of molybdenum disulfide flakes on a silicon substrate. And our image contrast is improved by the chemometric tools. And what I hope you'll see is that the Raman imaging is quite complementary to the optical microscopy that you see. All right, now what is Swift? Swift is the acronym for Scanning with Incredibly Fast Times. And it basically involves the detection and hardware communication, meaning communication between the camera and the electronic stage and its motion, to enable per pixel measurement times as fast as 7 milliseconds. So what we have then are measurements that are done on the fly. This stage is continuously moving, and the stage speed is calculated from the acquisition time that's set, so it's controlled by the camera, and you have a synchronization signal sent from the stage to the CCD. And computer memory is used to store the spectra, and the data are transferred over a high-speed USB connection, and the shutter is kept open throughout the entirety of the data acquisition. Now that we've briefly discussed the important considerations for Raman imaging and some of the experimental details, let's take a look at the results. In the lower right-hand corner, here you see a reflected light image of a flake of molybdenum disulfide on a silicon substrate. So here's the disulfide, and the dark area, which is a little bit out of focus, happens to be the silicon substrate. In the upper left-hand corner, you see the entire hyperspectral data set of spectra collected over this 10 micrometer by 10 micrometer area in 300 nanometer increments. And in the lower left-hand corner, you see the Raman image of this particular sample generated by the red and green brackets, where the red bracket is surrounding the single Raman peak of silicon, and the green bracket is surrounding two of the peaks of the molybdenum disulfide, these two here that you see. And this spectrum in the upper right hand corner is the so-called cursor spectrum. That is to say, that spectrum corresponds to the spectrum or the spectrum associated with the location of the crosshairs in either of the images below. So now we see silicon, and now we see essentially just the molybdenum disulfide, and we get to the edge, then we see some silicon coming through. So the important consideration right here for you is that the image was generated in 300 nanometer increments with 1 second integration time, and so this entire image took 22 minutes and 59 seconds to generate. And this is what you see using the peak bracket method. Now, if we click on an area here, let's click on the silicon, and we then highlight the cursor spectrum, we can then use the classical least squares fitting routine, add the silicon spectrum as one of our components, and now we go back here and find basically the molybdenum disulfide, add that component, and now you see we just so readily then can form a Raman image based on not the bracketing of the peaks, but classical least squares analysis of this image. All right, so let's go back to our hyperspectral data set. This is for 1 second. Now let's look at the results from a 100 millisecond integration time. And so let's run again our classical least squares. And we just enter that. Click on an area of molybdenum disulfide. Enter that component. And there you see the image. And let's now move on to and this is a 100 millisecond integration time per point. Now let's look at 50 millisecond integration time per point. And so you see the signal to noise is dropping because of our lower integration time. However, in situations like this where you basically have good chemical contrast, shall we say, between the spectral information of the silicon and the molybdenum disulfide, then the signal-to-noise ratio that one needs to produce the image is not as great as one might expect. Okay, so now we again generate our classical least squares image. Okay, there's our silicon component. And now our molybdenum disulfide component. And again, this is for 50 millisecond per point integration time. So that's pretty fast imaging. And let's drop it down now to 10 milliseconds. So we went from 1 second to 100 milliseconds, and now we have 10 millisecond per point integration time. So we're starting to reach probably the limits of what we're able to do with this particular material system. Nevertheless, as we see that the signal to noise has been dropping, of course, with the decreased integration time, we can still, based upon the entire spectrum and using classical least squares, we can generate our images based on the spectral contributions. And now we click on the molybdenum disulfide component. And so here then is our classical least squares image in the middle for a 10 millisecond per point in integration time. So here's 10 milliseconds per point, 50 milliseconds per point, 100 milliseconds per point, and 1 second per point. I hope by going through this demonstration here you could see the importance of the chemical contrast as manifest in the different spectra, and how if one has that, then the opportunities for fast Raman imaging are indeed great. All right, now that we've seen the data collected and had a discussion then about the extraction of spectral information from the spectra to render the Raman images, let's make a summary, or let's summarize a comparison of Raman images that are based on the bracketing of the Raman peaks, and then in the next slide we'll show a comparison of the images based on classical least squares analysis of the hyperspectral data sets. And so what I hope you can see here is that in moving from 1 second per point at a total of essentially 23 minutes of integration time to a tenth of that time, 2 minutes 45 seconds, where you go to 100 milliseconds per point, down to 50 milliseconds per point, you can really cut your times and still maintain pretty decent imaging. And finally, at 10 milliseconds per point, we're starting to get some fairly grainy image, which is consistent with the signal to noise of the spectrum. And that's the important thing to remember here, is that when performing imaging based on, say, a single spectral peak or two adjacent peaks, as we have done today, then more so than ever, the quality of your image and the contrast of your image, the signal to noise of your image, is really based upon the signal to noise of your spectra. Now, here are those same data sets treated to classical least squares algorithm, and you can see that if we now incorporate the entire spectrum in this CLS routine, we really don't lose nearly as much of the quality, the contrast, and the signal to noise in the image as we go from 1 to 1 second per point to 100 milliseconds per point, all the way down to 10 milliseconds per point. So just take in for a moment the difference here. We're talking about an image that required 23 minutes to generate here, and down here 47 seconds. That's a pretty substantial improvement in speed for being able to generate the images. So let me conclude then by saying that, again, in understanding Raman imaging and fast Raman imaging, the important consideration is that the greater the contrast in chemical bonding and solid-state structure will lead to greater spectral contrast, which of course leads to better contrast in the imaging. And the greater the spectral contrast, the faster one is going to be able to perform that imaging. And finally, the use of swift mapping, wherein the sincerity or the synapse camera is controlling stage movement and is communicating with the stage such that you have constant stage motion and timing of the camera with the stage motion, with the shutter always open, gives you a real significant improvement in your speed for fast Raman imaging. If you have any questions about the material presented here or the work that was done, please don't hesitate to contact me at 732-494-8660, and my extension is 8103. Thank you.